So let me start by thanking the organizers to give me a chance to talk about our locally acting mirror Hamiltonians. So let me start by asking a bit kind of provocative questions. Like, do we really have to consider photons when we model the quantized electromagnetic field? So I know this is a single photon workshop, but let me ask the question nevertheless, and let me explain why I'm asking this question. So when you look at Maxwell's equations in free space, then what you see is they are local equations, so they're in position space. Sometimes it is useful in classical electrodynamics to look at them in Fourier space, actually quite often, of course. And this is very consistent with the fact that when we describe the quantized electromagnetic field, then we assume that the basic building blocks of light are photons. They are the basic energy quanta of the electromagnetic field, and we use photon operators to describe the field. Actually, when you go in Fourier space, Maxwell's equations become a lot simpler. They look much nicer, but nevertheless, we always write them down in position space. And one of the reasons is that, for example, when you look at a wave packet, the dynamics of wave packets is very simple in position space. Everything that happens is the thing just moves with the speed of light, and the dynamics is almost trivial. Let me give you another example where in classical physics we use position space, so we use the Maxwell's equation as they are. For example, when we model light scattering by mirrors, we can of course write them down in terms of non-local wave packets, non-locally spread out waves, but that's not always the best way of modeling light propagation. So what we usually do when we describe mirror scattering by mirrors in quantum physics, there are different ways of doing it. But probably the most standard way is to introduce, not to consider all photon modes, but to introduce a subset of photon modes. For example, if I have a semi-transparent mirror, then what I will do is I will decompose whatever wave packet I have coming in into these triplet modes that Cornelia and Mandel introduced. That works really well as long as light is not approaching the mirror from both sides. Then I might have some interference problems and get some unphysical effects in this way. Another thing I can do is I can describe the mirror with Green's functions, and then take care in this way if I introduce correlations between all positions left and right and link them to the different photon frequencies. If I use these correlations, I can make sure that I never have light on the other side of the mirror and model it. But if you model light scattering by a mirror in classical electrodynamics, we do something much simpler. What we usually do is we use a mirror image method, and what you do is you have a wave packet. It approaches the mirror, which is in this case this is our mirror. So the wave packet just comes in, it approaches the mirror, and as soon as it touches the mirror surface, the mirror will change the wave packet into its mirror image. The mirror image is created, and then the mirror image is what moves in the opposite direction. So in this case, it becomes a much simpler description. And the question that we are asking here is, can we do something similar for mirrors? So we know how to model light scattering on the quantum level by mirrors. But what I'm hoping for, and what we were hoping for, is that we get a much simpler, more direct insight if we describe mirrors in position space and not in momentum space, so not in terms of photons. In order to do this, what I have to do is I have to first quantize the electromagnetic field in position space. So that's what we will do in the following. We will introduce highly localized field excitations, and then the idea is to, instead of having, for example, Green's functions, we will look into trying to obtain a Hamiltonian that first one that moves the wave packet, and then one that turns it around, some interactions that turn it around. Yeah. So let's look for Hamiltonians. It is also in some sense for a theorist, it's not very satisfying if every quantum system has a Hamiltonian and then there is one quantum system where we use indirect, more complicated methods of describing the system at the quantum level instead of using Hamiltonians in a more straightforward way. Okay, so let's have a look at field quantization in position space. So I will slowly walk you through this. So what we assume in the following, and that's more or less one of the very few assumptions that we need to make, is we assume that the basic building blocks of the quantized electromagnetic field are highly localized field excitations. And what we will do is we will describe them by annihilation operators, similar like we use photon annihilation operators. And in order to have a full characterization of these highly localized field excitations, what we need to specify is we have to specify whether the wave packet moves to the left or to the right. So you can check that quite easily what happens to your wave packet. You just have to put the detector on the left or on the right of your wave packet. Then you need to specify where your electric field is pointing. So you need to specify polarization. And then you need to specify where you are at a certain time. Yeah, and these annihilation operators are, they work in the Heisenberg picture. Then there are some no-go theorems. And also, if you think a little bit about it, these wave packets, they cannot be particles. We cannot count them. So for example, they do not correspond to energy eigenstates. They have well-defined energy expectation values because we can measure energy densities locally, but they do not correspond to energy eigenstates. They have no charges, they have no mass, so we cannot count them. So they're not particles. So we have a bit of a problem because normally what we do is we map everything, we map the field on harmonic oscillators, and now we can't do that because there's no position operator for photons. But this does not matter because we know a lot about them. We know already that they move with the speed of light and they have a very straightforward dynamics. And if we take also the symmetries of the electromagnetic field into account, we have enough to go on and to get a full description of the electromagnetic field in position space. So the first thing we derive is, the first thing we obtain is we observe that light moves with the speed of light. And that immediately tells you that an A is lambda of x and t, so that this operator has to be the same as A is lambda of x minus SCT. S is the direction where your wave packet travels in. The same has to apply for the equation operators. And because we want that the highly localized wave packets, they are the origins of electric and magnetic field amplitudes, that suggests that they are directly related. So if we want to write down an electric and magnetic field operators, we just superpose, in this case, I look at light propagating along the x-axis. So we put in field vectors in the y and the z plane. Here, the factors in the front have been chosen such that we later discover all standard theory quite easily. I will say more about it when we get there. Yeah. So the interesting thing is that as long as everything moves with the speed of light, you have a strong relation between position, time, and time derivatives. They are automatically linked, and these two equations automatically obey Maxwell's equations. We don't need to make any other assumptions apart from having this as our equation of motion. Yeah. So we already have field operators. Now there comes a slightly tricky bit. So what we also have, so let's assume we have a wave packet sitting here, and that wave packet moves to the right. And then we have a Hamiltonian for it. So I'm asking the question now, what does the Hamiltonian look like? So then we have a generator for the dynamics, and we want to describe the wave packet again by a Schrödinger equation as normal. So then this wave packet travels, if it's right moving, it travels here. If I have a left moving wave packet that has exactly the same shape and it moves, and I take a movie of it, then the movie will show this wave packet moving here. But if I show this movie, the recording of this situation and a recording of this situation, and I show this recording and play it backwards in time, then what you see is that in both cases you have exactly the same generator for the dynamics. But in one case you have time being positive, in the other case you have time being negative, and that tells you when you change the direction of motion for your wave packets, your dynamical Hamiltonian, the Hamiltonian in the Schrödinger equation, has to change sign. Yeah, so that means we can describe light by a Schrödinger equation like everything else, but we have to allow for Hamiltonians that change, that have positive and negative eigenvalues. Okay, so, and this is exactly what we find, because what we can do now that we know electric and magnetic field observables, we can calculate what the energy observable of the electromagnetic field is. What we need to do is we just need to integrate over E squared and B squared, and we get a Hamiltonian that has only positive eigenvalues. It's always positive, so the energy of the light that we're describing here of the wave packets is always positive, like you would expect, because it's also positive classically. But our Hamiltonian is one that now has positive and negative eigenvalues. So the Hamiltonian is the generator for the dynamics, so it changes sign when we change the direction of a wave packet. And at the same time, so I haven't written down all the details, but what this Hamiltonian essentially does, it takes a wave packet that sits here, annihilates it, and then recreates it a little bit later. And then as they get created, destroyed and recreated at different positions, that's how the whole thing then moves with the speed of light. Okay, so what we have now is we have all the field observables, we have energy observables, and we have a Schrödinger equation for light in position space. So I have a nice description that I can play with, and I could construct mirror Hamiltonian. But one of the questions that probably comes up first is, and I should address, is how does how does all of this relate to the standard description that we usually have? Yeah. So one thing we can do is we can do something that we do also in classical electrodynamics. We can write these annihilation operators for highly localized wave packets. We can write them as a generalized Fourier transform over operators that have that are bosonic. Yeah, so we can write them as superpositions of bosonic annihilation operators, and these have to be characterized again by the direction of motion, the polarization, and K. So K is usually related to the frequency of photons. And what we then noticed when we do this, so this transformation works. If you want this transformation to be unique so that you can invert it, so that you can also write your A as lambda of K as superpositions of A as lambda of X, you need to do what we do whenever we write down Fourier transforms. You need to start your integration to go from -infinity to infinity. Yeah. So in this notation, the direction is always given, the direction of motion is always given by S, and K is related to so S times K is the actual wave number, but K can now be positive and negative. So positive and negative frequencies have to be taken into account. One thing we do is if I want this transformation to be consistent with the equation of motion, so all wave packets moving with the speed of light, then I immediately see that the Hamiltonian for these bosonic operators has to have this form. And that's exactly the standard Hamiltonian that we always use for photons in free space. The only difference again is that we now integrate over a K that goes from -infinity to infinity. And we don't have only positive eigenvalues, we have positive and negative eigenvalues, but that's okay because we gave up on the energy of the system and the dynamical Hamiltonian to be the same. One way of getting this transformation is you could just write down the electric field and the magnetic field observables in momentum space and compare the expressions, and you see that these expressions that we get by introducing A as lambda of K, we get a description in momentum space, in photon space, that looks essentially exactly the same as it always looks like. as long as we look at only positive k, so if we look only at positive k's and we choose our f of k in a certain way, then we get exactly the expressions that we always have. Then all these extra terms go away and everything looks exactly as it always looks like. And also the energy observable is again the same as the dynamical Hamiltonian. So what we have done here is we effectively have doubled the normal photon space. So we have now more parameters, more inner degrees of freedoms for describing photons. Because we don't consider only positive frequencies, we also allow for negative frequencies. In terms of expectation value, what we have introduced is a kind of redundant description, because we now have wave packets that we have now different states for wave packet that have exactly the same field expectation values. But as I said before, we need to consider the negative case in order to have a to be able to change from momentum into position space and back. And this also affects the commutators. For example, what we have now is we have electric and magnetic field amplitudes. They always commute, which means they can always be measured simultaneously, which is not always the case in when people look at photons and not take all degrees of freedom into account. Okay, you're probably asking why I'm doing this, but as I said before, we're looking at photons, at mirrors. Maybe just one comment before I look at mirrors. There are already some experiments with, which which confirm the existence of photons with negative frequencies but positive energies. There's an experiment that has been done in St. Andrews, where they scatter light of a rapidly moving mirror and they get different blue shifts depending, or different Doppler shifts depending on whether the photons that they have created have positive or negative frequencies. Okay, but I promised to talk about locally acting mirror Hamiltonians. What we already found is that we now have annihilation operator with, or we can describe these highly localized wave packets. We know we have a dynamical Hamiltonian that moves these wave packets in any direction you want them to go. So the only thing in order to get a mirror Hamiltonian is we now have to introduce some local interactions that change the inner degrees of freedom. So if a photon comes, it flips it around and changes the direction of motion. And writing down such a Hamiltonian is quite relatively straightforward. The only thing we had to do, so what we assume in the following is we model the mirror that we have here, yeah, so this situation, we assume this is a big macroscopic object. So like when we describe lasers interacting with atoms, we assume that this gives us a classical potential. What happens is that the photon that comes in, when it sees the mirror interface, it will get annihilated and will be created somewhere else. So we allow for non-local couplings within the mirror surface, which is completely consistent with people looking at Green's functions where everything correlates with everything. But what we can show is, so what the mirror does is it takes a photon that moves to the right and recreates a photon that moves to the left. Yeah, so you have a scattering process. But when you take this Hamiltonian and you look at it in the interaction picture, you find that that you only get resonances when x is equal to minus x. That means the only resonant process that happens in the mirror is once the photon hits the mirror, it gets annihilated and it gets recreated at minus x, and then it moves in the opposite direction. Yeah, so this is the coherent process. And this will happen until the photons are all out of the mirror again. So we end up with a very relatively simple Hamiltonian, and we more or less get something that reflects really well what we observe in classical electrodynamics, where we use a mirror image method for modeling light scattering by mirrors without having to go into complicated equations. Let me, just because it's easy to calculate, we can also use our Hamiltonian to calculate the overall transformations for mirrors. And what happens there is you can exact whatever, independent of whatever mirror potential you write down, you can always calculate the scattering Hamiltonian. I guess, I'm not sure how much time I has left.
Yeah, time is more or less over right now, so maybe you can come to an end, please.
Yeah, I come to an end. So we can always calculate the scattering operator, and we always get the normal beam splitter transformation. So what I showed is we quantized the electromagnetic field in position space. So we derived all the observables just from symmetries and basic principles. And what I would like to emphasize that this is possible if we take positive and negative frequency of Maxwell's equation into account. So you have to quantize both, and then you're allowed to also quantize in position space. Here we only use this to construct locally acting mirror Hamiltonians. But the idea that photons might have extra degrees of freedoms like negative frequencies hopefully will give us also new applications for single photon-based quantum technologies, just to connect it back to the topic of the conference. But there are, of course, many interesting questions related to causality and the foundations of quantum physics as well. Most of the work that I talked about is within these papers on locally acting mirror Hamiltonians. It's on the archive, and we're working on improved versions of it at the moment. And there's a lot of work on negative frequencies. There are a lot of controversy or discussions, and very recent papers also on this topic by a lot of other authors, and I didn't go into the details there. Yeah, thanks.
Yeah, thank you very much. So let's open the microphones.